So again, love to introduce our next speaker. Our next speaker serves as the adjunct assistant professor at the University of Pennsylvania. He received his PhD in computer science from the University of Colorado Boulder and has over 40 plus peer-reviewed publications. He holds over 50 patents with over 100 patents pending. Wow. Please join me in welcoming the principal AI scientist and the director and founder of the machine programming research at Intel Labs, Justin Gottschlich.
Great, thanks, Artie. First of all, thanks so much for having me here today. And it's wonderful actually to follow right after Chris Ray, especially based on the stuff that he was ending on, which is focusing on self-supervision, because that's actually going to be one of the topics that I discuss in the talk that I'm going to give now. So let's go ahead and dive right in. The quick overview of what I'll be presenting on is broken down to, I'll give a little bit of an insight into machine programming research at Intel. Then I'll, as per always, talk about the three pillars of machine programming. And then we'll move into the bifurcated space of MP. And then we will give some examples of the emphasis of machine programming systems at Intel. And then we'll walk through just one concrete example, which is the self-supervised system called ControlFlag that we recently built. And we've got some exciting data, I think, to share with all of you today. So for some of you that may not be aware, machine programming is different than machine learning. It's principally about the automation of the development of software, and as a byproduct, the automation of the development of hardware. And MPR, Machine Programming Research, which is the group that I oversee, is a new pioneering research initiative at Intel Labs. Well, what that essentially means is that Intel has made a commitment to this research area for the long haul. And the long haul in this case probably means several decades. Is that we have a very aggressive and a bit audacious charter that I'll talk about in just a second. And we think it's going to take quite a bit for us to achieve all those things. But as we'll see today, that there are incremental improvements that we can make along the way that I think can be viable systems used in industry starting immediately. Very similar to what we're seeing like with Snorkel. So the goals of the two core tenets of MPR really break down into time and quality. So as we are working toward automating the development of software and hardware, what we want to do is achieve at least 1,000x improvement in programmer productivity, or oftentimes I'm now referring to these as software creators, because my belief is we'll move away actually from traditional programmers in the sense we're writing code, and we'll start doing more advanced things that allow people who can't code the ability to create software. Similar to some of the stuff that you're seeing with GitHub Copilot, where you can use natural language in the form of comments, and then out pops a synthesized program that fulfills the semantics and the intention of those comments. So this is the time aspect, is to reduce the overall time it takes by 1,000x. But if we're just synthesizing a bunch of software and the quality of the software that we're creating isn't maintaining some level of bar that we have, it's probably not helping us too much. So simultaneously, as we're focusing on improving the time it takes to develop software, we want to ensure certain quality characteristics that are going to be based on the domain for the software that's being constructed are at some quality level. And so some of those things are performance, correctness, security, maintainability, so on and so forth. And while it may seem as though this idea of reaching these two things, essentially getting 1,000x improvement in our productivity, and then simultaneously achieving superhuman ability in the quality may not be possible, we actually have early evidence that shows that this can be done for some constrained spaces. So for example, if you look at Maz Ahmad's work that was published just a couple of years back on automatically translating image processing libraries to Halide, what you see is that using a fusion of various machine programming techniques that are both stochastic and deterministic in nature, which we'll get to in a second, they were able to achieve a transpiled system that had a geometric mean speed up of 3.36x, which basically means they saw a 200%, so on and so forth, improvement for these transpiled systems. And it was done in an order of several hours in terms of, instead of what one might expect if a human were doing it, that might take potentially months, maybe years. So the three pillars of machine programming now, to switch gears, is kind of the basis of all of the work that we do in machine programming research. And this is a joint work that we published in 2018 with our colleagues at Intel Labs and MIT. And the three pillars are in front of you here. I'll quickly describe them, and then we'll talk a little bit more about them throughout this talk. The first is intention. Intention is principally concerned with the idea of finding novel ways or simplifying the existing ways for humans to express their ideas to machines. And this is really important if we want to get this productivity boost, right? If we can express ourselves to machines in a faster, more productive way, we'll probably become more productive. Intention is also concerned with lifting the semantics of existing code. For example, in the data that I just showed you from the work from Mazamad, they're actually taking existing code, finding a way to lift the semantics in a higher order lambda calculus, and then once the semantics are lifted, then they're able to transpile that to another form and make that code hyper efficient. So intention is principally concerned with these two things. Once intention is known, we move into what we call the invention pillar. Invention is really oftentimes not inventing too much. In many cases, what it's really doing is taking these existing components and it's combining them in novel ways to fulfill whatever the user's intention is. That being said, there are a couple cases that I've seen in the literature where invention is actually inventing what I believe is truly novel. And what I mean by this is it's inventing something that historically the human race, at least what's been documented, hasn't been discovered. And one example of that is potentially the autoperf system that we published at NeurIPS 2019, which is able to automatically synthesize performance regression tests that are able to identify parallel performance bugs that many of the other existing systems couldn't. So if they couldn't, an autoperf can. The idea is perhaps autoperf is actually inventing something that's truly novel. Now, once you have invention captured, and keep in mind, invention, what we generally want with inventive systems are a higher order representation of the program. We want it to be devoid of system level details. And this is fundamentally important because if we miss this aspect, then those systems tend to be hard to maintain. They tend to lose their portability. And they also tend to restrict the machine in the way that it can explore solution spaces and algorithmic rewrites when it moves into the adaptation pillar. So you have a higher order representation from invention. And now we move into adaptation. Adaptation then is principally concerned with taking that higher order data structures and algorithms and then adapting it to various hardware and software ecosystems. So for example, if you were to implement a sort that's going to sort like a couple kilobytes of data on your mobile phone, you might implement it one way. But if you're going to write a sort that's going to sort maybe several petabytes of data on a data cluster, that sort is probably going to be implemented in a very different way. And so this is why it's very important to have sort of the separation of invention and adaptation. But as is apparent with all the other talks that are given today, the fourth sort of hidden pillar in the three pillars of machine programming is all about data. And in fact, as Chris was describing and the other speakers were describing, I think Alex captured this very well, is data is sort of the essential element for all of these machine learning systems. And in fact, for machine programming, which is a space that I've been working in for probably the last 6 or 7 years, there's not a single machine programming system that I'm aware of that's able to do something interesting without some form of data. So we'll talk a little bit about how we can get around some of the issues that we have with data, and there's a lot in the space of machine programming. Now that you have a sort of general understanding of what the three pillars are, I think it's important to talk just briefly about what we describe as a separation of concerns, especially with separation of intention. And the idea here is When we separate intention from invention and adaptation, we restrict the programmer or the software creator from over specifying details that can then be confusing to the machine to think that they are actually part of the semantics of the program. For example, if you're writing a program and then suddenly you want to do some sort of optimization for like x86 or ARM or something of that nature, and you embed that into the intention, suddenly now that code becomes a little bit more challenging to be portable, to do algorithmic rewrites. So, what we want to strive for as we move forward is looking into advances in what we refer to as intentional programming languages, because we believe that these types of languages will help us in many ways. First, it will likely improve our productivity because we're only specifying intention and not the other lower level algorithmic and data structure details or system level details that are specific to software and hardware ecosystems. But in addition to that, it frees up the machine to then more thoroughly explore different types of solutions that if you overspecified those details in the intention, it would likely be bound to that and it wouldn't have the freedom to more exhaustively explore this. And the example here is if you look at Adobe Photoshop version 21, the example that I showed previously with this data is they're doing just that. Is the halide programming language and verified lifting, which are the two core techniques that essentially allow them to get this speed up, are both very intentional by nature. So verified lifting is trying to extract out the semantics in a formal way, and then halide is trying to separate out what the algorithmic details are from the scheduling details. And if you're interested in learning more about these things, I encourage you to take a look at this paper, and I think that it's very inspiring on seeing some of the results that we can get when we separate intention from these other pillars. Now, one thing that I think is very important to understand when we think about machine programming is not a rebranding of machine learning, and it's also not ML for code. So I have lots of colleagues that are at various academic institutes and in industry, and some of them will say to me, "Oh, well, Justin, at Google we call this ML for code or whatever," and that's great. I think that there is certainly an ML portion to machine programming, but there's also a deterministic side, and this is the side that uses things like formal methods, SAT solvers, SMT solvers. And what we tend to find is that historically in the space of program synthesis, if you don't have deterministic systems, you can't necessarily guarantee correctness the same way that you would be able to if you just built a stochastic system. So oftentimes what you'll see in today's MP systems that are purely stochastic in nature, like GitHub Copilot, is it will give a recommendation on what it thinks the code should be based on the natural language you provide, but it needs a human in the loop. A human must be there to then verify that. However, with the formal methods, the deterministic side of things, it tends to not require that because it is going through some formal mathematical proof, like the work of verified lifting, is that it's doing the semantic lifting to a higher order lambda calculus. It then formally verifies that those semantics are representative of the original program. Now, in this talk, we're going to principally focus a little bit more on the stochastic side. And I think that as most of the audience is aware, when we build these stochastic systems, machine learning or machine programming, they tend to improve with more IID data, independent, identically distributed data. And so we can look at this a little bit more as we look at the concrete example, but I want to now show you one concrete embodiment of what a new type of approach for machine programming looks like that takes these stochastic and deterministic systems and then gives them a concrete embodiment. And one example is neuro-symbolic research. So Armando Solar Lozama, a professor at MIT, recently launched a new 5-year NSF Expedition Center called Understanding the World Through Code. And principally what the center is about is taking these two sides of machine programming and fusing them together. That one embodiment of it is you'll have a neural side, which is shown here on the left, using traditional machine learning techniques with a machine learning neural network that's actually generated from some large amount of data. And then simultaneously, it will fuse what is more of the classical systems using program synthesis techniques in the symbolic space, is that it will take perhaps significantly less data, use a formal synthesizer that has some sort of verification on it, and then out pops a program. And what I'm seeing in the literature, which is really exciting, is that a fusion of these two systems simultaneously lead to some really exciting results. So hopefully now you have sort of an understanding of what machine programming is, what the three pillars of machine programming are, and then a concrete embodiment of what I mean by the bifurcated space of machine programming. So at this point, I can go to some of the efforts that we're working on at Intel. I only have time really to talk about one, but I want to give just a little bit of an overview that machine programming is really taking off at Intel. We probably have hundreds, maybe thousands of people working in this space today. For my team, we're principally focusing on debugging, profiling, and productivity. And so those first three systems you see there, ControlFlag, MISM, and AutoPerf, are all systems that we built out of our lab. And we'll be talking a little bit more about ControlFlag, but there's other efforts that are going on. I want to make a quick call out to Intian, which is a new venture that's being led by Intel. I think it's wholly owned by Intel at this point. And they're also working on machine programming systems that are doing things different than some of the historical ML solutions that are doing things like neural programming, where the neural network replaces the code. Intian is still using machine programming and is still using machine learning, but the output is not a neural network. The output is actually code. And part of the reason for that is, as some of the prior speakers noted, is understandability can be often really important. So interpretability. When we have a neural network, sometimes it's challenging to understand. But if we have human readable code, instead of like retraining a whole model, because when we have a bug, if we have code, we could potentially go tweak one line of code and then suddenly everything's good. So this is just a short list of some of the things that are going on, but machine programming is definitely being embraced at a very large scale at Intel. Now, going back to Alex Ratner's introduction, I want to just quickly draw attention to the MISM system that we recently built. MISM is a code semantic similarity system that basically has both a stochastic and a deterministic component on it. The deterministic component is we invented a new structural representation to lift the semantics out of the code that we call the context-aware semantic structure, or CAS for short. Is very much inspired by the fantastic work from Berkeley and Facebook on their Aroma system. But it also has a stochastic component. And the stochastic component is it has a neural engine that then allows it to learn based on the repository that it's being trained on to augment the way that it generates a similarity algorithm. And that part is really important. What's interesting, I find, with MISM, to sort of reinforce the importance that I think Chris Ray was making and Alex was making, several others have made, is that the more data we have, we tend to see better results with these stochastic systems. So in the first line, you see that when we had MISM compared to the state of the art, we were able to get approximately 2x better accuracy across about 400,000 programs. And these were all labeled. So going back to the idea of the need for labels, obviously something very important. The second analysis, which was done independently by IBM and MIT in their CodeNet project, is they showed that MISM compared to the state of the art was actually up to 5x better, but their data set more than doubled. And so we haven't done a deep analysis yet of these results, but our sort of knee-jerk intuition is that one of the big factors here is that the data size has doubled, therefore it's giving MISM more information to learn from, and then that is likely to be one of the fundamental reasons why MISM's accuracy continues to improve, whereas the other systems don't have that stochastic element, and so they stay sort of at this baseline level. But now I want to talk a little bit about what Chris was getting into is what can we do without labeled data? And this is a new system we built called ControlFlag. We published this paper earlier this year at MAPS, the new machine programming symposium. And it's principally about helping us in debugging. So to first quickly motivate why we think debugging is valuable is if you look at a study that was done by the University of Cambridge back in 2017, they break down the cost of software development and they effectively show that 50% of software development is debugging. Now, these numbers here, the 1.25 trillion, this is back in 2012 or so. We did a sort of back of the envelope calculation, and we believe that it's approximately around 3 trillion today. So that means about $1.5 trillion are being spent in debugging software today. So if we can reduce the time it takes to debug software, we're likely going to have a pretty good impact. So let's dive in on how you might start to debug systems using machine programming. Well, one of the areas is we can do pattern recognition. And essentially, we can try to identify when we find anomalous code segments. And anomalous code segments, in many cases, will lead to stylistic differences. They could be potential defects. They could be security vulnerabilities. And all of these things can delay the delivery of your software, result in loss of customer trust, and so on. A concrete example of what an anomaly looks like is we ran ControlFlag on curl, which is a piece of software that's been around for 30 years. And supposedly, according to the curl team, it's been in, I believe it's used over 1 billion times a day. So we were really surprised when ControlFlag was able to flag this line on 360, which says, this S keep on is greater than true. For those of you who are programmers in C and C++, you probably know that the value false is 0 and any non-value is true. So if any non-value is true, what can be greater than true? So we then reported this to the curl team, and you can see sort of the interchange we had with them. At this point, we hadn't disclosed ControlFlag, so we didn't tell them how we found it. But they confirmed and said, actually, yes, this is not right. Let's go ahead and fix this. And they came up with their own solution, and now that has been integrated into the mainline. Now, there are existing code anomaly detectors that are out there and different ways that we can detect these things. So oftentimes we'll do things like unit tests, various quality assurance type of engineering. And then there are these static analyzers, compilers, and linters. And we've used these pretty effectively. In Intel, many of the industrial partners we work with, Microsoft and Google, so on. One of the limitations, though, is first, they require that a human manually write these rules, which I think is something that Alex hinted about, how this whole idea of writing rules can be problematic as you want to scale systems out. The second is the manual effort can potentially be error prone. So even if you are writing the rules and you think you've got it right, you might actually get the rule wrong. So how do we overcome this? Well, we overcome it by, at least one potential attempt is with ControlFlag. So in front of you is a very high level diagram of how ControlFlag works. It's a self-supervised anomaly code detection system. And the core idea is that with only using a small amount of metadata in the repositories that we're mining on GitHub that give us some confidence level of whether we can trust them, we then send ControlFlag out to then learn about control structures in these programs. It essentially is given no guidance in terms of there are no fixed rules. We don't tell it what anything means. We just tell it what a control structure looks like and that it should learn what it sees as normal and learn potentially what it finds as abnormal. The takeaway of its design is essentially twofold. First of all, it's self-supervised, so it doesn't require any labels, which is really nice. This is one way we're sort of circumventing the lack of labels on code that exists today. The second is it's self-evolving. So as we throw more data at it, it continues to get better and better. We took ControlFlag, which we invented, I think, last fall, and we had the Neurogen, I think, had the first prototype done in the early spring, and we trained it across 6,000 GitHub repos, trained it on slightly over 1.1 billion lines of code. And then we tested it against a number of open source repositories. And what's interesting is that even the ones that we think are very hardened, like Git, for example, it was able to still find some anomalies that had been overlooked. And thus far, we haven't reported each one of these anomalies just due to lack of bandwidth. But every anomaly that we've reported to the open source community, they have acknowledged that it is a defect, and then they have corrected it and then pushed it into their mainline. But we're also looking at proprietary deployed code. So this one I think is of particular interest. What you're seeing here is ControlFlag. This is obfuscated code. I can't tell you where this code came from, but what I can tell you is it's proprietary and it's deployed. There's actually 3 different bugs in here that ControlFlag was able to identify. The first is very simple. It's a copy-paste error on line 11 and line 12. This is basically just if you updated line 11 or 12 and they're not perfectly in sync, you'll have a potential bug. That's not really that big of a deal. The second is on line 14. I can't go into too much detail of it, but basically, if the value that's being stored in this array is 2, it will pass the mod 4 check as a non-zero value, which will go into that P32 assignment. Because it's doing a pointer 16 offset by 1, it'll jump by 2 bytes. When you dereference the P32, you'll get a 0, and then that'll crash, segmentation fault. It's unlikely for this to occur, but it's still a crash bug. But the third is a bit terrifying. The third is a security vulnerability in line 11. What's happening in line 11 is that's not actually a fixed array. It is a dynamically allocated array from a pointer, but there's no bounds check on that index. This has been confirmed by the group that owns this proprietary software, that we realize that this is a legitimate defect that could be a security vulnerability. It could jump to confidential data. You could actually root a system with this. If I'm a smart programmer, I can get it to jump to a specific location that will then execute my own code, and I can take ownership of your machine. So this is one concrete example of some of the things that ControlFlag was able to find. If we take a larger look at that first repo, we scanned this number of files. It took approximately 3 hours. ControlFlag is highly parallelizable, and it found 104 confirmed anomalies. We looked at a second repository across 10 million lines of code. It was able to detect 191 anomalies. And according to sort of like these back of the envelope calculations, it's our belief based on working with these partners that we are saving on the order of hundreds of millions of dollars because these are in deployed pieces of software. So in conclusion, what I briefly spoke about today is sort of make you aware of the machine programming research charter that we have at Intel. We talked a little bit about the 3 pillars and how separation of intention and lifting semantics from code is important, that we think that the future is intentional programming languages, things like Halide and SQL, which are declarative or maybe slightly intentional, but we expect to see more of that. We tried to go over the bifurcated space of machine programming to talk about how it's stochastic and deterministic. It's not just stochastic. It's not just ML for code. That deterministic part is super important. And then we also look at one example that we worked on called ControlFlag, which is a self-supervised system for machine programming. I also would quickly like to blame Alex Ratner. Hopefully, Alex, you're on the line. Alex is a good friend of mine. I've been working with him for several years. I've been trying to get Snorkel to build out support for machine programming to do automatic labeling for at least 2 years, and it still has not existed. So I was forced to invent ControlFlag to overcome the lack of labels, and it's my hope that Snorkel folks will work with me to get support on the labeling that we're looking for. So this is my little jab at Alex, and hopefully a slight encouragement to the Snorkel team that we love weak supervision. We don't have enough labels, and it would be wonderful if Snorkel could support automatic semantic labeling for code. And then lastly, my team is hiring. So if you have a PhD and you're interested in this space, please let me know. We will be teaching machine programming fundamentals at Berkeley and MIT this fall. Actually, MP has been taught for several years at MIT already. And then lastly, if you're interested in this stuff, you can stay current with our machine programming website and various YouTube channels. And then lastly, we'll be talking about machine programming in the Intel Innovation event on October 27th. And with that, thank you so much. Back to you, Artie.
Thank you so much, Justin. That was an amazing talk. Great to learn more about your work. I think a lot of us have heard of like Codex, and it came up in the media recently, and it was really great to learn that it's not just stochastic approaches, but the deterministic approaches as well. So that was definitely a new learning for me. And for our attendees, Justin has discovered a new way to get the entire Snorkel team's attention. Just come be a speaker and ask for support from the Snorkel team. So that's something you're interested in. Please volunteer to be a speaker at our future events.
My goal has been achieved, Artie.
Exactly. I think a lot of people did pick that up. So we have a lot of exciting questions that have popped up in the chat that I'd like to ask you. So Samdan asks, is it possible to fix the bugs automatically since you're also just, detecting them?
Yeah, absolutely. So right now, ControlFlag is both stochastic and deterministic, but we don't quite have the verification that we believe is necessary for the deterministic side in to do the automatic mitigation of those defects. Our goal, though, as this question asker quickly, gets to the heart of, is we do want a closed loop system. And we provide recommended fixes today in ControlFlag, but we still require human verification. Once we add the formally verified component, it's our belief that we can then start to automatically mitigate those. So then it'll identify them, it'll root cause them, and then it'll fix them without any humans.
Wow,
Excellent
that'll
question.
be really exciting and bring down debugging time very effectively. So really excited to see more there. Next question we have from Parth. He asks, wouldn't it be more beneficial to also consider the intent of the code to identify bugs rather than just the irregularity? Or is it the case that 80% of the bugs are just identifiable by irregularity independent of the intent?
No, so whoever asked this question, I love this question, and the truth is, what he or she is suggesting is a much harder problem, but is what we're trying to do. So our next step is we want to fuse ControlFlag with MISM, because MISM can lift semantics, and then we'll be able to gain understanding of the semantics of the code, and then see if the semantics then deviate from what would be expected. So ControlFlag is doing, in some sense, this sort of very basic, naive analysis of things, which I think this question asker noted, and that the future is really what he or she mentioned, that we want to be able to do this analysis on a much deeper level, try to understand the semantics of things, and then find much more complex bugs. We're just not quite there yet.
Makes sense. Lots of exciting future work in the area. This seems that a lot of our question askers have picked up on as well. Next question we have is from Vashisht, who asked, how costly is it to label, I suppose it's 1 million examples, examples for MISM?
So the truth is yes, this is a great question. I don't actually know the answer. What we did is we used several open source projects that had automatically been labeled. And I think some of them came from some of these coding contests. So one of them was POJ 104. I think that had several 100,000 labeled examples. Another was from Google Code Jam. That also had, I think, maybe upwards of millions of examples. And then the new one is Project CodeNet from IBM and MIT, and they've done the labeling. The truth is, we think that the manual effort to do the labeling, especially because we anticipate the semantics are going to be at various levels, is likely to be massively time consuming. So the idea of doing it manually seems basically intractable for us.
Hence the call for support for Snorkel. It all adds up and makes sense.
It all makes sense now, right, Artie?
Well, thank you so much again, Justin, for taking the time to be here with us today and teaching us so much about machine programming.
Thank you so much for having me. Yes.
Of course.